In this video, we will look at how to determine if the number of arrangements is a combination, a permutation, or something else. And we'll start with fundamental counting principle. To find the total number of arrangements, you identify how many possibilities there are for each item in the arrangement. Then you multiply these numbers of possibilities together. We will look at the three different scenarios. In the first scenario, the order of the arranged items matters, and repetition is allowed within the arrangement. In the second scenario, the order of the arranged items matters as well, but repetition is not allowed within the arrangement. In the third scenario, the order of the arranged items does not matter, and repetition is not allowed within the arrangement. We'll look at examples of each of these three scenarios. In our first example, a person makes up a password consisting of 6 characters. That may be a lowercase letter, an uppercase letter, or one of 10 different numbers, 0 through 9. How many passwords are possible? And the questions we ask, how many choices are there for each character, and can we repeat the characters? Well, for each character, we can have 26 lowercase letters, 26 uppercase letters, or 10 digits 0 through 9. That makes a total of 62 different choices for each of the characters. Can we repeat the characters? Well, yes, we can, because it's always permissible to repeat letters or numbers in a computer password. So this gives us 62 choices for each of the 6 characters. And using the fundamental counting principle, we just multiply those values of 62 together. But we must also answer the question, does the order of the arrangement matter? Well, if you switch 2 letters or numbers in your password, you know it doesn't work when you try to use it. So yes, it matters. And that means we don't have to divide our answer by anything. So our answer is 62 multiplied by itself 6 times, or 62 to the 6th power. And that gives us 56,800,235,584 different passwords possible. On to our next example. A group of 5 children are given 5 different gifts. How many ways are there to give these gifts if each child gets 1 gift? And note that there are a total of 5 gifts to give out. The key statement here is that there are a total of 5 gifts to give out. That means we can't repeat gifts. One child gets a gift, and there's 4 gifts left for the next child. So there cannot be any repetition here. So we get 5 gifts for the first child, 4 gifts for the second child, 3 gifts for the third child, 2 gifts for the fourth child, and the last gift for the 5th child. And now I ask, is the order important? Well, try switching the gifts after you give these out to the kids. They have different gifts. And what do you think will happen? There'll be some arguing. And yes, the order is important. So using the fundamental counting principle, we have 5 times 4 times 3 times 2 times 1 equals 120 ways of giving these gifts. And since the order is important, we don't divide that answer by anything. This actually is a permutation. It's a permutation of 5 things taken 5 at a time. You can use the permutation formula shown here, or just reason it out with the fundamental counting principle as 5 times 4 times 3 times 2 times 1. In our third example, 3 lucky kids are selected from a group of 20 to go on a field trip to an amusement park. How many ways are there to select these 3 kids? Well, there's 20 different choices for the first kid, 19 for the second kid since 1 is used up, and 18 for the third. And we can't have repetition here unless we did some cloning. So no repetition. Then we ask the question, is the order important? Well, if you selected 3 kids and their names were Ann, Bill, and Sue, if you just rearrange the names on that list, Ann, Sue, and Bill, Sue, Bill, Ann, and so on as I have shown here, it's the same list. So the order of those 3 names does not matter. It's like the problems where you pick a committee. So that means when we're listing all these possibilities, we're getting 6 possibilities for each actual unique combination. So we have to divide by 6. So we divide our answer by 3 factorial, or 3 times 2 times 1. Otherwise, we'll end up getting 6 times too many names. So our answer is 20 times 19 times 18 divided by the 3 times 2 times 1, and that gives us 1,140. And this ends up being a combination of 20 taken 3 at a time. And the way I like to remember combinations is permutations divided by r factorial, where r is the number of items or people chosen. So in this case, we have a permutation of 20 taken 3 at a time divided by 3 factorial. And here I have a resource that might be real helpful for you. It's a calculator, but it's not just a calculator. It allows you to designate whether the order is important. And here I'm doing a combination of 5 taken 3 at a time, so order is not important. And also repetition. And for combinations and permutations, repetition is not allowed. And here I have the problem, the combination of 5 taken 3 at a time. And it not only finds my answer of 10, but it allows me to list all the possibilities here. And I used for my 5 possible names Sue, Ann, Bill, Fred, and Mary, and it listed all 10 different combinations of them. And you can see that they're all different, and it accounts for the fact that order is not important. So this is a real nice calculator to use, checking your answers as you do homework and just getting a better understanding. It also has some links to more information on combinations and permutations.